Hi, I would like to demonstrate the installation, running, and application of Prom. The Prom installation files, including the MATLAB installer, are available in the Prom folder here. So if you don't have a MATLAB installer yet, you just open this folder and then run the application installer. For that, you might need to have administrative privilege. Once you run the application installer, you can go back and open the Prom folder where you find the Prom executable file. You double click that and the Prom will load and open the user interface for Prom. So here is the interface for Prom. Let me minimize the other parts here. So Prom has this user interface where you have the project, opening new project, and saving project. Then you have the input menu, analysis, the assessment, optimization, and distribution modules included here. So for this illustration, I will start by simply by importing the input file. So the first input file would be the flow data for the Mara River Basin, and I have those files included in the installation package. So you have the Mara River Basin flow data. Then it will import all the flow data that are available in there. In the meantime, once the flow data is loaded, we will need to load the demand data. So the demand data is prepared in Excel file where you have the demands of individual subbasins, subbasin 1 to subbasin 12, arranged by months. This is the total volume of demand estimated for each month in 3 different blocks. So for block 1, which is the environmental demand, is here. Block 2 is available here, and block 3 is here. We don't need the total demand because the Prom estimates the total demand by adding the individual blocks together. Okay, now we have the flow data for all the subbasins in the Mara River Basin. The subbasins are shown here in a map where we have 1, 2, 3, 4, 5, 6, 7, 8 to 12 of the Mara River Basin, and we'll use this numbering to build the network, the flow direction in the system. Alright, let's import the demand data. So this is the interface to import the demand data. Once we have the demand in Excel format, we just have to bring it and paste it here. Before that, let me take you a little back. In the user interface at the beginning, we have this exceedance specification where you specify at what percentiles that you wanted to extract the flow. So we have the 95 and the 80%. So from 100 to 95 we have one block, from 95 to 80 we have another block, and from 80 to 0 approximately we have a third block. So that gives us 3 blocks. So the analysis would be based on these 3 different blocks. As you have seen, they are the environmental demand, the domestic demand, and the agro-industry demand. Okay, going back to the demand input. So the first block would be the environmental demand, where we have 12 nodes, 3 blocks, and because we're using months, we have 12 time steps. That goes from January to December. Okay, so putting the demands is pretty easy. All you have to do is go to the first one, select from January to December, and copy, and you go to the demand interface and you simply click paste once you check the block number. So this is the first block, click paste, everything is here. The next would be block number 2. Then you go to the Excel file and select what belongs to block 2, copy, and paste. And for block number 3, again we go to the Excel, demand estimates, copy, and paste. So we have all the demands for every subbasin from 1 to 12 and every month. Update the demand file, accept and close. Okay, we don't need this Excel file anymore. Now we have demand and we have flow. So you can look at the different statistics of the flow. You can look at the descriptive statistics for A1. Now, from January to June, you can see the mean median for the first subbasin, or you can have it for all the subbasins. These are just descriptive statistics that you can look at for the flow data. So the next step is building the flow direction. Now we have 12 nodes. So once we have these 12 nodes, we have to specify from what node to what node. If you remember, or if and the figure of the Mara River Basin that I showed you earlier, 1 and 2 both flow to 3, then 4, and then 8. So 4, 5, 6, and 7 all flow to 8, then the rest will just follow the number. So 1 goes to 3, you just type 3, and 2 goes to 3, 3 goes to 4, and from 4 is 8, and 5 also flows to 8, and 6 flows to 8 as well. 8, 9, 9 to 10, 10 to 11, and 11 to 12. So once we have this order, we generate the direction matrix. So this will be used for water balance in the optimization and in the assessment process. Save and close. The next step is the flow duration. So these are the flow duration curves for each of the subbasins from 1 to 12. You can look at individual curves for A1. So these individual monthly flow duration curves are for the first subbasin A1. You can also look at what January of A1 would look like. So you can explore the flow duration curves for all of them. The next step is to estimate the available resource. So that will be based on the cutoff percentiles that we have specified here. We can look at for all subbasins. So this is the subbasin estimated available resource for the first block. You can also look at for the second block, and you can also look at how it looks like for the third block. So these are volumes extracted from the flow duration curve, and after the water balance or the water budget is done based on the direction matrix that we have provided. The demand volumes that we have input at the beginning for block 2 and for block 3, and then you have the total as well. So you can look at the values, and you have this map. You can rotate this map to look at the 3-dimensional view of the available resource and the net demand. Once we did this, the next step would be to specify the DSR range. So the minimum DSR here is 0, the maximum is 100, because we are looking for the percentile of DSR. For the Mara River Basin, we used 4 intervals, and the minimum volume is useful to avoid division by 0. Let's put 0.001. Whenever the flow volume is really low, that value would be assigned. So the first is from 0 to 10. That's a very low, that's a low water stress. And this next is from 10 to 20 as presented in the paper. And the next one is 20 to 40. That's a high water stress. And then 40 to 100. these are the utility indices attached to this interval. So the first utility index is 0, and the next is 1, then 2, and then 3. These are the same values as specified in the manuscript. We update the DSR. Now we can do the assessment. We will look at the DSR distribution by block. So the DSR, this is for the total, and we can have for block 1, block 2, block 3. Now we will look at the current utility indices. This is again the figure, and we can look at the map, the status map for the first block. That's the environmental demand, and then the domestic demand. This is the status of the resource, the baseline status of the resource. This is for the third block, and this is for the total resource. If we are satisfied with this distribution, then the assessment process ends here. But if this is not good enough, for example, when you look at the first block, there are a lot of reds here, which is highly stressed, and you look at 2, there are yellows here. So there seems to be a potential to improve. There is a lot of low stress in the agro industry demand, in the third priority demand. So we can optimize this and see if there is any improvement that we can make by reallocating the water. So the next step is the optimization, where first we set the DSR values. So as specified again in the previous manual, in the previous manuscript, I believe we had let me check where we had those values. I believe that the first one goes from 1 to 60 with an interval of 5. So with this we generate alternatives. So this is the minimum DSR, the maximum DSR that defines the feasible space. So the feasible space for optimization, and this 5 is the interval between successive DSR. So the first is 1. In the manuscript we have an equation that specifies Z. So Z1 is 1, then Z2 is going to be 1 plus 5, 6, and it goes on following that. Let's preview. So these are the number of feasible combinations of DSR that we are going to run for optimization. So we have 2,197 alternative scenarios that we are going to run based on this setup. We update the DSR and then run the optimization. So this is the sum of the utility indices, and these are the reliabilities. So these curves show the result of the optimization process. So from 1 to 60 with an interval of 5, we will look at here. So for block 1 the reliability is 78, for block 2 69, and for block 3 72. The optimal DSR is 6. So if 6 is the optimal DSR, then we can further include 6. The next one was 6 plus 5, that's 11. So we can run from 5 to 12 because we know the optimal is 6, and then there is a potential that it could be 7, 8, 9 because we didn't run for those values. So the second optimization would be, this is refining to exactly find the optimal combination of DSR, because we went in an interval of 1, 6, and 11. So let's start with 6 and go up to 11, and this time let's go with an interval of 3. So for this is a refined interval, again 216 possible combinations, and then we run the optimization. So as we have predicted earlier, the better optimal location is not 6, rather it's 9. But still we went through an interval of 1, so we can still improve that interval into 0.1. So from 9 to 10 we have 8, 9 and 10, and 9 is the optimal. So let's take a new scenario where we can go from, let's say, 8 to 11, and we can have an interval of 0.1. This will take a little bit longer because now it's going to be 29,000. So I would rather put 8.5 and 10.5, and that will reduce the number of iterations that we will run. So update, so accept, and we run the optimization. So the finer the interval that we take, the longer the program takes to process. Therefore, it's better to have an optimization process that keeps narrowing down around the previous optimal result. So it's a successive optimization can reduce the computational time. Okay, so now we have 9.9 as an optimal solution, where we can see how the reliability has improved from 78 to 82 here, and from around 69 to 73, and from 70 to 77. At this point, it would be, this can be considered as an optimal solution. So for that optimal solution, we can run distribution of water, or we can simply look at how the status have changed. So we can look at the optimal DSR now for block 1. So this is the optimal for block 1, and we can also look at the optimal UI, which is easier to see. So all the rates that we have seen before at the baseline optimization are now changed into white. So that's a big improvement that came with the optimization process. We can also look at 2 and 3. If we are satisfied with this optimal solution, we can conduct, or we can do the distribution. Now water is distributed, and we can look at the optimal resource volume. So this is the volume allocated for block 1 and block 2 and block 3. We can also look at the flow distribution for block 1, block 2, block 3. We can look at individual sites where we can extract the hydrographs. For A1, for example, this is the total flow, out of which when you divide it by individual block, you have the blue for block 1 and block 2 and block 3. Block 2 and block 3 are almost the same. And we can also look at by months, individual months for block 1, block 2 and block 3. And we can also look at the optimal flow exceedance for every block, or for all the blocks. So these are the exceedances for block 1, block 2, block 3. You can have them in line plots for individuals, or bar plots for individual months. Okay, these values can be exported into table. So basically this is what Prom can do. Thanks for watching.